This video is about moles, which you should have learned in honors or regents chemistry, but also about dimensional analysis, a specific way that we use math to help us solve chemical problems, and not just chemistry, but also physics if you take that in the future, or any other higher level science classes. Most of them use this thing called dimensional analysis to help you analyze or look at your units to make sure that you know how to work with your numbers. So first off, every video I'm going to show you what you should have been able to do. So you should have already been able to explain the unit of a mole and calculate the molar mass of a substance, but we will go over that, and use significant figures to round calculations. I don't have a specific video about sig figs. We're going to be using them throughout class. And by the end of this video, you should be able to use dimensional analysis to calculate the moles and the mass of a substance. So when I say you should already be able to, if at any time in the school year you see a bullet labeled this, and you can't already do it, you need to catch up. And some things you could do is come to extra help and ask questions, search for videos online, which I don't know how much I recommend. You have to make sure that they're a reputable source, or ask me for additional videos that I can send you. You can use textbooks and review books, which I have in class for you to review, and you can find old Regents or honors package you might have from years prior to help you catch up, right? So if you see something that you don't know how to do already, this is really important that you take the time to fix your learning. Also, whenever I say something that needs to be memorized in class, which is hopefully not too often, but near the beginning of the year there's quite a bit, it will be in this yellow color. So if you see this yellow color, definitely write your notes and star it, and make sure you start studying it every night. Any questions, you can always chat me on Remind or Canvas as soon as possible. And in each video, I'm trying to have a question of the video which focuses you on why we're learning this. So my question of this video is, what does 4 birthday balloons, a sip of water, and 40 nails have in common? And by the end of the video, we're going to answer that. So in order to answer that, we need to talk about stoichiometry, or the math of chemistry. And it really comes down to this mole number, which represents 6 times 10 to the 23rd particles. And those particles can usually be atoms and molecules. Remember that atoms are one individual particle that might represent just one element, whereas a molecule means that the two elements are combined to make either a compound, or you can talk about diatomic molecules, which we'll come back to, but something like O2, right? There are two particles stuck together. So atoms are smaller, thus the smaller word, and molecules are slightly bigger, thus the longer word. Make sure you write about that if you didn't know it. So the mole being equal to 6 times 10 to the 23rd, that number comes from the fact that in what we call carbon-12, there are actually 12 grams of that substance. When you accrue it, it actually has 6 times 10 to the 23rd particles. And in order to compare one sample to another, you should never compare their masses, because you can accrue any mass you want of any substance, right? You need to accrue the same number in order to compare them. I want to compare all of my dollars to all of Bill Gates' dollars, right? The number of dollars we have, which is obviously not comparable, right? But not necessarily other things about them, right? And the molar mass, also known as the gram-Fuller mass or molar mass, is the mass of 1 mole of a substance. And elements' molar masses are reported on your periodic table. So they're listed right on the periodic table. For example, if you look at your periodic table in the middle and they ask you what iron is, you can see it's right there, 55.85 grams per mole. That's the gram for a mole. You can mass any amount of iron you want, but if you want particularly 6 times 10 to the 23rd particles, so you can compare it to something else, you'll need to grab 55.85 grams. Similarly for copper, which happens to be in the same little row there, you would say 63.55 grams for every mole that you have of copper. So what you say is, if I have the same number of particles of iron and copper, copper will always weigh more because it weighs more per mole. Also, a little note, last year we used to talk about rounding to 1 decimal place, though you can still do that in most cases. I'm going to recommend that you use every single number and round at the end of your calculation. It works with better numbers, like better math and better accuracy. So try to report every single number. You can also do this with compounds, as long as you know what the formula is. So when you say water is made out of hydrogen and oxygens, you would also need to know that it makes out of 2 specific hydrogens and oxygen. And I think most of us know that. So if you know H2O, that means that there are 2 hydrogens and an oxygen stuck together. So I did 2 1.008 masses and a 16 mass for oxygen, for a total of 18.016 grams for every mole. So you can see that if you have the same number of particles of water as you did iron and copper, it weighs even less, right? So making sure that you know this is always for that 602 times 10 to the 23rd number. Another example of something like that, calcium chloride. Some of you might have forgotten that calcium is a +2 ion and chloride is a -1 ion. So when they combine, they make CaCl2. If you don't know that yet, there is an upcoming video that reviews that. But for now, if I told you it was CaCl2, you should be able to take the calcium's mass, 40.1 I wrote here because I rounded, which is okay. I don't recommend it in the future. And chlorines, there are 2 of them at 35.5 each for a total of 111.1. Now, if I had not rounded, I would have had one more significant figure or number in my numbers. Instead of 111.1, I would have had one more decimal place further, ending in a 3. So maybe you could be more accurate if you and more specific if you use every single number. From there, we want to know the mass of different moles. So instead of just saying I have just 1 mole, what if I had 6 moles, which really means 6.02 times 10 to the 23rd particles 6 times, like almost the same as if you had a dozen, it means 12, and if you had 6 dozen, it means a dozen, a dozen, a dozen, a dozen, a dozen, a dozen, or 72 particles, right? So we're saying we have 6 packages of neon, and how much would that weigh? Most students know that they could just take the neon mass on the reference table and multiply it by 6. And that's fine, but we're going to see some really more tricky examples throughout the week, next 2 weeks, I guess. And you want to be able to do dimensional analysis then when it gets really tricky, because then it actually is easier using this method. Where these easy problems we're about to do now, you might be like, this method is so silly because it's too easy. I could just do it in my head, 6 times neon. Yes, but we're going to do the easy problems using dimensional analysis, so when the harder problems come up, we already know how you do dimensional analysis, okay? So what we're going to do is we're going to start with a number over 1. So see how it's in yellow? That means you should memorize this. We're going to put 6 moles over 1. Then we're going to multiply by a new fraction. And I wrote multiply in capital letters because you don't want to press an equal sign in between. That means you're setting up proportions. We're not doing proportions. Next, we're going to place a conversion with the same unit on the denominator of a new fraction. So if you make a new fraction, moles was on the top of our first fraction, so moles will be on the bottom of our next fraction. Moles and moles will be catty-cornered from each other so that they will cancel when you multiply across. You don't want to put moles on the numerator because you would get something like mole squared when you multiply. No, 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 no. So moles on the bottom, so they'll cancel. What we're saying by conversion factor is something where its numerator is equal to its denominator. So we need to know, if I want to get it out of moles, moles goes on the bottom, but what is 1 mole equal to? 1 mole is equal to, on your reference table, 20.18 grams of neon. Remember, we just showed how to find that. It's on the periodic table. So we're going to do 6 times 20.18, which is what we were saying before, but this is a setup for that type of calculation. And so we multiply across the numerators and divide by any denominators, which happen to be 1, so they don't really matter. And we'll get an answer of 121.08 grams. So that's the setup, and hopefully you can pause the video and write your notes down. But also, we need to talk about your significant figures as we go. So the number 6.00 has 3 important numbers listed, or else I would have just wrote 6. And the 20.18 has 4 significant figures, or 4 numbers that are pretty important. And when you're multiplying or dividing, you're dividing or multiplying and rounding to the least number of sig figs. So if there's only 3 sig figs in 6.00, I should only have 3 sig figs, or 3 numbers, in my 121.08 grams, which currently has 5. So that's right now what we call calculator garbage or calculator vomit. And we want to fix that so it's a little less specific. We really don't know that much detail. And so if I only want to pick the first 3 numbers, that would be a final answer of 121 grams. All right, let's move on to another problem. Calculate a mass of 0.023 moles of what we call ammonia or floor cleaner, NH3. So again, some people know that they can just multiply these moles by how much NH3 weighs on the reference table, and they'll be done. But that won't show us how to do dimensional analysis for harder questions in the future. So again, using those rules, we're going to place the 0.023 moles on the top of a 1 with the unit, because you're analyzing your dimensions or units. We're going to multiply by a new fraction, putting the same unit on the denominator of the next one. So moles are catty-cornered. We need to decide what numerator that denominator is equal to. So what's 1 mole equal to? Well, if you look up nitrogen, which is 1401, and hydrogen, which is 1.008 times 3, you get 17.034 grams. And now we're going to multiply the numerators and divide the denominators to get a big calculator number of 0.391782. You're not going to write all of that down, but now that we showed the math, let's do our sig figs. 0.023 moles has 3 significant figures. It's the 2, the 3, and the following 0. The zeros in the front of a number don't count because they can be changed if I change it to something like millimoles or scientific notation. So preceding zeros don't count. At the end of a middle of number, they do. So 17.034 has 5 numbers. That 0 is trapped. Ending zeros count if there's a decimal. So I have 3 sig figs in the first mole number and 5 in the gram number. I'm going to go by least sig figs and give myself 3. So that means I'm going to do 0.39, and that 1's going to become a 2 because of the 7 after it that rounds it up. Normal rounding rules that you've done since you were in 4th grade. Let's do another one. We're going to go backwards this time. We're going to figure out how many moles there are in 8 grams of helium, because that will take us to how many particles there are in the future. So if I have 8 grams, I'm going to place that over 1. We're going to multiply by a new fraction. This time the fraction's denominator is going to have grams in it because we want the grams to be catty-cornered from each other. And we want to say how much grams is equal to a mole. So I had looked up on helium, it weighed 4 grams per mole. So now again, the numerator and denominator are equal to each other. A mole is 4 grams. The grams are catty-cornered from each other. So what that means is we're going to divide 8 by 4, and we're going to get 2 moles. Some people had already known that because they were able to do it in their head. They're like, hey, helium only weighs 4. I have 8 of them, so I have twice the amount that I should have, 2. But again, we're also looking at how to set this up for future problems. Not only do we want to do that, but check sig figs, 8.00 specific 3 by 3 numbers. 4.00 specific by 3 numbers. So I want 3 numbers, and the way we can do that is add on some decimal places and put our unit, so 2.00. Let's do one more. 8 grams of CCl4. 8 grams goes on the top of a fraction over 1. Multiply by a new fraction where we know the numerator and denominator are equal. The grams have to be catty-cornered. Sorry, I didn't write the G in, and I really should have. And then 1 mole is equal to 153.81. That came from carbon plus 4 chlorines, right? So I had added that on the side. We're going to divide 8 by 153.81. What we can see is we don't have anywhere near a mole. A mole is 153, and I only have 8. So I have a decimal amount of moles, which is okay because this is a large, big number of particles. And so I have 0.520, blah, 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 super number of sig figs, when all I really know is that I have 3 numbers that are important here and 5 that are important in 153.81. Notice I'm missing the ones that are not really something to look at. So if I only have 3 in 8.00, I'm going to only have 3 in my grams number, which changes it to 0.0520 grams. Again, zeros in the front don't count. Zeros at the end count if there's a decimal. So just to summarize, if you haven't written the notes already, you always start with a number over 1. You multiply by a new fraction and place a conversion factor where the denominator is the same unit as the numerator of the first fraction. You're going to multiply numerators and divide denominators. And maybe if you haven't already copied this down, you should by now. Back to the question of the video, what does 4 birthday balloons, a sip of water, and 40 nails have in common? Well, each 1-liter balloon has approximately 1 gram of helium inside. So if you have 4 balloons, you have 4 grams. And 4 grams is actually equal to a mole of helium on your reference table. A sip of water is on average about 18 milliliters. The density of pure water is 1 gram for every milliliter. Therefore, a sip of water is 18 grams as well. And that's actually equivalent to a mole of water, which we had done earlier. So you probably see where this is going. Each iron nail, it weighs about 1.4 grams. If you had 40 grams nails, you do 40 times 1.4, and you get 56 grams, equivalent to, oh my god, you guessed it, a mole of iron. So what we're trying to say is that 4 balloons have the same number of particles as 40 nails and a sip of water. Each of these have the same number of particles regardless of the different masses and volumes that they have accrued. At this point, you should be able to use dimensional analysis to calculate the moles and mass of a substance.